The kinetics of radioactive decay going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in this lesson we're simply going to cover the kinetics of radioactive decay. We're going to introduce the equations here governing the rate of radioactive decay. We'll talk about the decay constant lambda. We're going to talk about what's called the half-life a little bit. And then we're going to demonstrate how to use each and every one of these equations and when you might choose one over another. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we're going to start this lesson off by taking a look at a plot for radioactive decay. We'll take a look at a plot of n, which is going to represent the number of radioactive nuclei you have, so versus time here. And you'll see that it doesn't decay linearly. It's going to decrease over time, but not linearly. Turns out it's logarithmically. Sometimes you'll hear this described as exponential decay. So now, even though it looks exponential decay here, or logarithmic, the way you know it really is if you actually take the log of this graph and plot natural log of n versus time, and if that comes out to a straight line, then this really was logarithmic. It really was exponential decay, if you will. Now, it turns out also that if you plot this natural log of n versus time, that the slope of this graph is equal to the negative of what we call the decay constant lambda. We'll define that here in just a second. Now, if we looked at the rate, so your rate is going to be the change in the number of radioactive nuclei that you have over a change in time. Almost. We also got to factor in this negative sign right here. And the reason we do that is if you look here, the amount of radioactive nuclei we have over time is going to be decreasing always during radioactive decay. And if it's decreasing, well, then that change is going to be a negative change. Well, it's customary to always define rates as positive numbers. And so in this case, if that's a negative number, then I got to multiply it by a negative sign out front here. That way the overall rate comes out positive. Now in chemistry, we would describe this as being a first order process. All radioactive decay is a first order process. And it turns out that your rate is going to be proportional. So actually, let's write this again. Your rate here is going to be proportional to the number of nuclei you have to the first power. And that's what it means to be a first order process. So not the biggest thing that's going to get a lot of airtime in a physics class, but if you've seen this in chemistry before, it should look a little bit familiar. And so it turns out the way you can write this then is that your rate, which can be written this way, instead of, in saying that it's proportional to n here, which we don't have to actually include that one, but what we can say then it's equal to n times a proportionality constant, which in this case we call lambda. Now in a general chemistry class, we generically used a lowercase k and just called it a rate constant. We use that lowercase k as a rate constant for any reaction. Well, here specifically, this is a very specific reaction for radioactive decay. And in physics, the decay constant is specifically represented by the Greek letter lambda in this case. Now, it turns out that what you have right here is what we call a differential equation. And it's beyond the scope of this class, but it turns out you solve this by what we call a separation of variables followed by integration. So, and when you do solve it, though, you get these two equations right here. So, and I say you get two equations. You only get one of them, technically. So you could say it's this one or you could say it's this one. It doesn't really matter. So because these are really the same equation just written twice. If you look, the first equation here with the exponential, all I've done is take the natural log of the whole thing in order to write it just like this. On the left side, we got natural log of n. And on this side, when you take the natural log of two terms that are multiplied, you can take it as two separate natural log terms that are added together. And so here we'd have the natural log of n naught plus the natural log of e to the negative lambda t. Let me write that once. Natural log of e to the negative lambda t. Well, the natural log and the exponential here are inverse functions. Inverse functions are ones that when you do one on the other, they cancel each other out. It's kind of like multiplying by a number and then dividing by the same number. Then you accomplish nothing. So same thing here. What you're going to be left with here after taking natural log of e to the negative lambda t is just minus lambda t. And that's why here when you take the natural log of this whole side, you get natural log of n naught minus lambda t on this side. And so this is really the same equation as the first one, just having taken the natural log of both sides. Cool. Now, if you're solving for n or n naught, this first equation is probably the more convenient one to use. because solving for n or n naught here kind of sucks because you're solving for something under a natural log. You can totally do it, and if you're really versed at math, no problem. So, however, if you're solving for the decay constant or time, it's probably easier to use this second one. That way you don't have to solve for something that's under the exponential. It's not in this second version. So it really depends on what you're kind of solving for, which of these you might use. Now, it's also customary, it turns out, to define for a radioactive nuclide what we call a half-life. So, and a half-life is just the amount of time it takes for half of a radioactive sample to decay. And it turns out for radioactive decay, these half-lives are constant. So, and that's going to seem a little bit strange here, because if you look at the rate here, well, again, we define rate as negative change in n over change in time. Change in n over change in time, that's rise over run, delta y over delta x. That's the slope of this graph, and the slope of this graph is not constant. It is constantly changing, so the whole time. So the rate of the reaction's changing the whole time. In fact, the slope's getting less and less steep the whole time because the rate is slowing down and it asymptotically approaches zero. So the rate is not constant, but this half-life time is indeed constant. You kind of see why this is. So let's say you started off with 16 radioactive nuclides. The half-life, again, is the time it takes for half of them to decay. Well, if half of them have decayed, so how many would that be and how many would you have left? Well, half of 16 is 8. This means that after one half-life, whatever amount of time that happens to be for this specific radioactive nuclide, 8 of them have decayed and 8 remain. And we're going to write how many remain here. That's after one half-life. Now, if that same amount of time passes again, a second half-life, well, then half of the 8 that you had here are now going to decay. That's 4 that are going to decay, leaving 4 left. And if you go through another half-life, then half of these 4 are going to decay. That's 2 that are going to decay, leaving 2 left. And so if you look, this is all the same amount of time. This period of time, this period of time, and this period of time, they're exactly the same amount of time because the half-life time, again, is constant. But if you look, during the first half-life time, 8 nuclides decayed. During the second half-life time, 4 of the nuclides decayed. And during the last half-life, 2 of the nuclei decayed. And so the rate really is slowing down. So by saying that the half-life time is constant in radioactive decay is not a contradiction in saying that the rate does indeed change and slows down over time. Okay, now it turns out you can do this in terms of the number of radioactive nuclides, but it turns out you can also do it in terms of, say, the fraction of radioactive nuclides that you have remaining, or the percentage, or even the mass, because it turns out that the mass of a radioactive nuclide is proportional to the number of the radioactive nuclide you have left and will decay and follow kind of the same exact principles. And so instead of using n and n naught to represent the number of radioactive nuclei and the original or initial number of radioactive nuclei, you could use it as the mass and the initial mass, since they'd be proportional as numbers, and still do all the same math with the same decay constant for that given radionuclide and things of that sort. All right, so this could have been 16 grams, and then 8 grams, and then 4 grams, and then 2 grams if we were dealing with masses instead, and it would have worked in principle exactly the same way. But again, you can also do this in terms of percentages and fractions. So if we do percentages first, you start off with 100%. Well, after one half-life, you'd have 50%. After a second half-life, you'd have half of the 50%, so you'd be down to 25%. And after another half-life, half of the 25%, you'd be down to 12.5%. So on and so forth. So, and again with fractions, initially you'd start with all of it, all one of it. After a half-life, you'd be down to a half. After another half-life, you'd have half of a half or a fourth. And after a third half-life, you'd be half of a fourth or 1/8, and then 1/16, and 1/32, so on and so forth. And one thing to keep in mind, so here we're showing you what is left, because we just keep cutting it in half based on however many half-lives you have. But you can also talk about how many radioactive nuclides have decay, or what percentage have decayed, or what fraction have decayed. And so in this case, all of these represent 3 half-lives. So here we started with 16 grams, once I changed it to mass anyways. We have 2 grams left. And the question would be, after these 3 half-lives, how many grams decayed? Well, all the rest. If 2 grams out of the 16 are left, that means the other 14 grams underwent radioactive decay. They decayed. Same thing here. If after 3 half-lives we have 12.5% of our sample remaining, that means that the other 87.5% decayed. Same thing here once again. If after 3 half-lives 1/8 of the original sample remains, that means the other 7/8 of the sample actually decayed. So be careful when you start cutting this in half multiple times based on the number of half-lives that have passed, you're always going to have what remains. And as long as that's the question, great. But if the question actually asks how much has decayed, you have to take the original amount minus what remains. The 100% minus the 12.5%, the 1 minus 1/8. So on and so forth, the way that works. Okay, one other last thing to note before we get into some calculations, that's units. Now it turns out that the SI unit for radioactive decay is called the becquerel. Or the becquerel, if you're French or something like that, and that just represents 1 decay per second. That is a becquerel. Well, it turns out historically, though, the Curies kind of came up with their own unit here, the CI, the Curie. And it's 3.7 times 10 to the 10th decays per second, or 3.7 times 10 to the 10th becquerel. It's not the SI unit, but it is one that is still routinely used for historical reasons. So you might have to do some conversions involving that as well. But the becquerel is the SI unit, and it's nice and conveniently defined as simply 1 decay per second. Let's do some calculations. So while we're going to do a single question, it is going to be a multi-part question, because I definitely want to demonstrate how you use each of these different equations and when one might be easier to use than another and things of the sort. So the first part of the question reads, fermium-253 has a half-life of 3.0 days. What fraction of a sample remains after 12 days? All right, so here we want to know what fraction, so we're going to start with all of it. Now, it turns out these calculations are fairly simplistic as long as the amount of time that's passed is an exact integer number or whole number of half-lives, as is the case here. So here we're told the half-life is 3.0 days for fermium-253, and the amount of time that's going to pass total is going to be 12 days, which notice 12 days would be 4 sets of 3 days, 4 sets of the half-life time, 4 half-lives. And we're just simply going to cut this in half 4 times. And so over the first 3-day period, from our 1, we're going to cut that in half. And over the next 3 days, after a total of 6 days, half of a half is 1/4. After the third half-life, another 3 days, a total of 9 days, half of a fourth is 1/8. And then finally, after a fourth set of 3 days, a total of 12 days, half of an eighth is 1/16. And that is the fraction that remains after 12 days, which again happened to be an exact whole number, 4 half-lives. If the question had said again, how much has decayed, or what fraction has decayed rather, it would have been 15/16, the initial minus the amount that's left after the 12 days. So not so bad as long as the amount of time that has passed is an exact integer number of half-lives. All right, next part of the question says, if the initial mass of fermium-253 is 64 grams, what mass remains after 12 days? So here I just want to demonstrate that you can again do this problem in terms of mass as well. And so if we start with 64 grams, well, again, we're still doing 12 days, which means 1, 2, 3, 4 half-lives. And we're just going to cut this in half 4 times then. After the first 3 days, we're down to 32 grams, just cut in half. After the next 3 days, a total of 6 days, we're down to 16 grams, cut it in half again. So after another 3 days, a total of 9 days, cut it in half again, we're down to 8 grams. And then finally, after the final 3 days, a total of 12 days, we're cutting that in half again and making it 4.0 grams if I want 2 sig figs to be consistent with the problem there. And there's the answer. So you can do it in terms of fractions, you can do it in terms of masses, and again, you could have done it as a percentage. So you would have found you'd gone from 100% to 50% to 25% to 12.5% to 6.25%, had you done it that way as well. All right, we're going to finish this off with the harder questions. So at least the last one's going to be the hardest of the questions. And the third question's not so bad. What is the decay constant? Now, it turns out for any given radioactive nuclide, they will have 2 characteristics that define them. So a half-life and a decay constant. Well, and it turns out those are mathematically related to each other. So you don't actually need to be provided with both. If I give you one, you can actually solve for the other. So because our half-life here is equal to the natural log of 2 over lambda, 0.693 over lambda. It's just a constant over lambda. So these half-lives, again, are constant for a given radioactive nuclide and only depend on the on the decay constant. So a constant divided by a constant is going to give you another constant. Now, if you look at where this half-life equation comes from, you can really derive it from this one right here. And so if I rewrite that, I'm just going to subtract ln of n naught to the other side. So you're going to have ln of n minus ln of n naught equals now negative lambda t. You might remember a property of logs that if you have two logs added, you can multiply them under a single log, or if they're subtracted, you can divide them under a single log. And so in this case, it's ln of the first over the second, again, is equal to negative lambda t. And if we talk about a half-life passing, so again, if I go from, say, 64 grams to 32 grams, n naught is the initial amount, 64 grams, n would be 32 grams, and this ratio, provided the amount of time that's passing exactly one half-life, is going to come out to a half. So, and it doesn't matter what you start with, the amount you'd end up with after half-life is going to be exactly half of that number. And so after a half-life, this ratio is equal to ln of 1/2, which is then therefore equal negative lambda. And don't have a variable anymore. The amount of time we've said we're taking is that half-life time. Well, it turns out that the natural log of 1/2 is negative 0.693. That's going to equal negative lambda times t1/2. The negatives will cancel and you rearrange this. And that's where this relationship comes from, where if you know the decay constant, you can solve for the half-life. If you know the half-life, you can solve for the decay constant. And that's exactly what we're going to do in this problem. The question is just, what is the decay constant? Well, we know the half-life is 3.0 days. So all we got to do is rearrange this a little bit to solve for lambda instead. And if we do that, we get lambda equals 0.693 all over the half-life of 3.0 days. And we'll let our calculator do the heavy lifting here. And what did I do with my calculator? Under the paper. All right, so 0.693 divided by 3. We're going to get 0.231. So, and this has units. Notice it has units of days to the -1. Now here's the deal. If I was going to do this in proper units here, I'd want to turn this into seconds and put this in seconds to the -1. That's most likely how it's going to be recorded if it's in SI units. But the truth is, these can be crazy amounts of time for the half-lives, so which would then be inputted into the decay concept and stuff like this. So for the half-life times, it would be ridiculous to put 3 days and record the seconds, and so you're more commonly actually going to see it as 3 days. But you can do all the calculations. You just got to be careful on the units when you do, as we'll see in just a second. So, but that is our decay constant. In this case, I probably only wanted 2 sig figs out of that. So, yeah, and so in this case, we'll take off that 1 and just leave it as 0.23 per day, if you will. And then finally, the last part of this question says, how much of the 64-gram sample remains after 5.0 days? And here's the hard question, because we know that, after the first 3 days, our 64-gram sample decayed down to 32 grams. And after the second 3 days of 6 days total, we're down to 16 grams. But the question's asking what amount is left after 5 days. And the problem that makes that difficult is it's not an exact number of half-lives, and not an integer number of half-lives. I know, though, that 5 days would fall somewhere in between here and here. This is how much I have left after 3 days. This is how much I have left after 6 days. It's going to be somewhere between 32 and 16, and probably a little closer to 16. And I can eyeball that number, but that's not an exact number. If you were taking a multiple choice test and there was only one answer choice between 32 and 16, you should just pick it and move on, and life is good. But if you have multiple answer choices in that range of 16 grams to 32 grams, you're going to have to do a little more math and use one of these 2 equations. Now, if you're solving again for lambda or t, you'll want to use the second equation. If you're solving for n or n naught, it's going to be easier to use the first equation. So, and that's what we're doing here. We're going to be solving for n, given that n naught is 64 grams. We know our decay constant now because we solved for it. So, and then we'll plug in 5.0 days. We just have to make sure the units on our decay constant and time match. Now, notice one thing. In the last question, I asked, what is the decay constant? The thing that could make this even harder is that they could give you the half-life, but never actually ask you that question. Just jump straight to this last question and ask you how much is left after 5.0 days. And that's the one that stumps a lot of students, because they don't realize that knowing the half-life, they know the decay constant. You want to know that. You know one, you know the other. And oftentimes the only reason they give you a half-life is so that you can figure out the decay constant if you're not going to be dealing with a perfect integer number of half-lives. And so had we not found the decay constant in the previous question, that would be the first thing we'd do right here, so that we could plug it back into this equation right here. And so in this case, n again equals n naught, e to the negative lambda t. So n is going to equal 64 grams. Again, we can use this in terms of mass, not just number of nuclei. E to the negative, and again, that's going to be 0.2 0.23 per day times 5.0 days. And the days cancel as they should. And once again, we'll let our calculator do the heavy lifting. So we're going to have 64 times the exponential, which is usually a second function of your natural log. And then I'm going to put parentheses, negative 0.23 times 5, and my parentheses. Oh, and it doesn't like my syntax. What did I do wrong? Oh, I used a minus sign instead of a negative sign. Let's try that again. All right, so in this case, I get 20.2647 grams. We got to first ask ourselves, does that answer actually make sense? Well, yeah, because I was expecting somewhere between 32 and 16 grams, and my gut was that because 5 days is closer to 6 days than it is to 3 days, that it's probably going to be closer to 16. And so 20.26 grams or something like that makes total sense. So, but in this case, I have a problem because I want 2 sig figs based on the numbers given. And so here I've got 20.26. And the problem is, maybe I'll round that to 20.3 for just a second. But to get that to 2 sig figs, that's going to turn into 20 grams, which I can either put the bar over it, or I can make that 2.0 times 10 to the first grams, which is kind of my preference there. Cool, and that is all there is to it. If you have found this lesson helpful, consider giving it a like. Happy studying.